All right, this is video 2 for the series and parallel unit. In this one, we're going to start talking about a different experimenter when it came to circuits, Kirchhoff. And what Kirchhoff allows us to do is study circuits that have more than one resistor in the circuit. And that's really, really important because, as you might imagine, most circuits, they have a lot more than just simply one resistor. Now, this will also allow us to be able to study circuits that have multiple branches. So normally, all the circuits you've seen so far had one path. Well, now we'll be able to take a look at circuits that have multiple paths. All right, the first law. This one really goes with resistors that are in series. And what I mean by series is that all the resistors are in a line. Now, what Kirchhoff's first law tells us is the sum of all voltage drops must equal 0. So it's a very simple thing. So here we have a circuit, and notice that the resistors are in series. They're all part of one line. So what Kirchhoff's first law tells us is that the voltage drop across each resistor must add up to the voltage of the power supply. Now, what that means is we consider the voltage drop across resistors to be negative. So right here, my EMF is 5 volts. So what I would write is I would say that my EMF minus a delta V1, and let's say delta V1 is the voltage drop across resistor R1, minus delta V2, where delta V2 is the voltage drop across resistor R2. And remember, when you go to measure voltage, you have to measure it across something. That all must equal 0. In other words, the EMF of the battery must equal delta V1 plus delta V2, and that might make a little more sense. And we've seen that also. We've conducted some simple experiments, virtual experiments, to see that. All right, now we can apply Ohm's law to this. Ohm's law says that V equals I times R. So for our EMF, I've got I times resistance. Now, that is the resistance of the entire circuit. And that's special. We call that the equivalent resistance. Also, current I will be the main current coming off of this battery. Now, remember when I had you conduct simple virtual experiments before, we saw that when these resistors are in series like this, the current remains constant throughout the entire circuit. So that main current stays the same. So in other words, that current would be through resistor R1 and resistor R2. Well, looking at this, seems pretty simple. This leads us to the idea that the equivalent resistance then, if we take a look at that, we see that the I's will all cancel. And that the equivalent resistance would equal R1 plus R2. And that's something that's very important right there. This idea of equivalent resistance, that's the resistance of this entire circuit. So whatever values R1 and R2 are, let's say R1 is 5 ohms and R2 is 15 ohms, that means the equivalent resistance would be 20 ohms. It would be the resistance of this entire circuit. If I were to take this circuit, I can boil it down to one 5-volt power supply and one resistor with that equivalent resistance. So these two circuits are basically the same thing. So then, for a circuit where the resistors are in series with each other, that means they're on the same line, the equivalent resistance would be the sum of all the individual resistors. So this symbol right here means sum, and I use a lowercase I for individual. So the equivalent resistance equals the sum of all the individual resistors. Using that then, we could calculate the main current flowing through the circuit. So the Ohm's Law says that the EMF equals the main current times resistance. So the main current would equal the voltage of the power supply divided by the equivalent resistance. That would calculate, that would give us a number for that main current. And then using the main current and the resistance of each individual resistor, we can find the individual voltage drops across each resistor and the power consumed by each resistor. So let's practice that. Let's take a look at an example. So here I have a circuit. It's got a 25 volt power supply. I'm going to call this one up here R1. So R1 is 65, R2 is 84, R3 is 73, and R4 is 10. What that also means is that I have 4 voltage drops. And each resistor is going to consume power. So let's make to get us started, let's make a little table to help us organize everything. So there's my 4 resistors. And let's have this fourth, or this last one down here, make this like our totals. So this would be where our EQ, our equivalent resistance, would go. Okay. So first thing we want to do is we want to find the equivalent resistance of this circuit. That equals the sum of all individual resistors. So for us, the equivalent resistance of the circuit then is 232 ohms. Now we want to use that equivalent resistance to calculate how much current is flowing through this circuit. So that's going to be 25 volts divided by 232 ohms. And that gives me 0.108 amps, or 108 milliamps. Now remember, because this is a series circuit, the current flows through it unchanged. All right. The next thing we want to do is we want to calculate those 4 voltage drops. But we have Ohm's Law, which says that uh, delta V equals I times R. Well, if we look through here, that means all we have to do is take the individual resistor and multiply that with each current. So we're just going to multiply across this table. So we got 65 times 0.108. And that is the voltage for each resistor. Now, as a way of testing this, I can add these all up. And when I add these all together, I get right around 25 volts. It's not perfectly 25 volts because I had to do some rounding, but it's pretty darn close. Because, and do this to prove it to yourself. Add these 4 numbers up to see if you get 25 volts. Lastly, we have our power. Well, power is current times voltage. I'll use my delta V for this one. So to get the power, we just have to take the current and multiply it to the voltage. And we can find the individual voltages for each resistor. Now, if I add these together, these 4 numbers, I get 2.71 watts. And if I were to take as a way of checking this, if I were to take my power, my current times my EMF, my 25 volts, again, I would get something that's very similar to this. So the overall power consumed by this circuit equals the power consumed by each of the individual resistors. Now, when we go to design a circuit like this, then, we have to make sure that each resistor can handle each one of these powers. If that power is greater than what the circuit or that resistor can handle, it will cause the resistor to malfunction. All right, this concludes video 2.